Now, this is, as you can see, part 0. It is very important because here we will talk about the source of relativity and why this source is untenable for trying to defend relativity. Alright, so the story starts with a guy by the name of Lorentz. Let's just call him Lorentz. Easier, right? So, he was a great scientist. There is no doubt about this. He is the first guy, well, typically recognized to be the first guy, who seriously proposed that atoms are made out of differently charged particles, and the oscillations of these particles produced light. However, he was a believer in the luminiferous ether, i.e. a medium that light traveled through. This is a problem. Because, as we know, Einstein is commonly acknowledged to have gotten rid of the luminiferous ether. Now, the Lorentz ether theory was created sometime between 1892 and 1895. It was synthesized between that period of time. So this was based on a completely stationary ether. The Michelson-Morley experiment was in 1887. So before this time. Now, Lorentz invented his transformations to explain the fact that the experiments of his time period did not agree with him. They told him that, no, there is no ether. And he said, no, there must be an ether. Therefore, I must invent something to make there be an ether. To make all these experiments still work, even with an ether. Well, I mean, this demonstrates some problems. First of all, it demonstrates that the Lorentz transformations were intended for a stationary ether. Lorentz also displays some other problems. For example, his schema, which is in psychology a term for basically a worldview, where you essentially take all the information that comes in and filter it through the schema before actually incorporating it. Which means that you tend to only hear what you want to hear. I only hear stuff that agrees with you, and immediately discard everything else. So, Lorentz, his schema was that there must be a stationary luminiferous ether, or aether, depending on how you spell it and where you are. So, schemas tend to remain unchanged by contradictory information. So what did Lorentz do when he got the information that, oh, our experiments prove that your stationary ether is impossible? Well, here we use the example of a child thinking there is a monster under the bed, i.e. Lorentz insisting that there must be a luminiferous ether. Alright, so the parents turn the lights on, i.e. Michelson and Morley and so on, do their experiments, and demonstrate that there is no monster. I.e., hey, we do not detect any evidence for an ether. In other words, we don't have an ether. What does the Lorentz do? Well, he could change his schema and agree that there is no ether. What he actually did was essentially take this information, force it into his schema, and say that, well, the monster runs away from light. Or invent his Lorentz transformations. So, given the fact that this is where Lorentz transformations came from, we should also point out that using them to defend relativity is a little bit amusing for the simple fact that Einstein basically took Lorentz stuff and made relativity from them. Well, okay, he added one thought experiment of his own, but hey. Another funny thing was that the original equations Lorentz had did not deny that you could find the ether. So Poincaré, or however you pronounce his name, Poincaré, whatever. Poincaré helped him adjust the formula so that, well, first of all, gravity was accounted for a little bit better, and the ether became undetectable. Much like Russell's teapot. Now, it is fair to say that there are teapots, many teapots, orbiting the sun. for the simple fact that many households on Earth have teapots and Earth orbits the sun. However, Russell's teapot says that, oh, it's not on Earth and it must be orbiting the sun somewhere way out in outer space. And he insists that, and if he had to insist that it was there, then it was just a matter of faith because it couldn't be disproven. Yeah, Einstein essentially took this same ether and made it this matter of faith. This diagram is in every textbook. This is Einstein's one contribution, his thought experiment. By the way, we proved in later parts that this is completely wrong. But let's look at Lorentz equations first. Do these look familiar? Well, they should. Einstein basically took these and made relativity from them. So the originality of relativity was just a matter of time. Somebody had to have their name on it. So Einstein got to be that guy. Einstein did, however, do something else that was very useful. He abbreviated Lorentz's relatively many assumptions to just two postulates. The first one is that all inertial frames are equally valid, essentially. So the laws of physics apply in all frames. All right, same thing. The point is that this is not debatable. Like, this is check. It must be correct. He also proposed that the speed of light must be constant regardless of the movement of the emitter or the observer. There are so many problems with this that it shouldn't be even started until a little bit later. We'll talk about it in greater detail in a moment. There were a few other unspoken assumptions, such as isotropy and homogeneity of space. No piece of space that light travels through is any more important than any other piece of space. So, here's a photo of Lorentz and Einstein meeting. And in around 1910, 1911, Lorentz delivered these sentences in lectures. He was a professor. He gave lectures, of course. So essentially, Lorentz said that because electromagnetic oscillations, i.e. light, as they understood it at the time, because they propagate, therefore, regardless of whether we call it ether or not, or ether or aether or whatever, there is something there. Now, if we don't like that name, we can use another word. These concepts are basically undoubtable. It is not up for question that in every theory, you must account for the fact that light can be transmitted without any observed medium. So either there is no medium, or we give it some sort of name, like quantum vacuum, or aether, or space-time, or similar. Now, in Einstein's time, he was considered the first to discard the notion of an aether in his special relativity. So this made him famous and special and so on. Yeah, the problem is that he definitely did not discard the ether. He even acknowledged later in conversation with Lorentz that yes, we may call it an ether. So space-time is a new name we used. We should point out that he did wait some years before publishing his general relativity so that people would recognize him as the guy who got rid of ether without just saying, hey, he just gave it a new name. Now, the most important problem with Einstein's ether, and the most immediately obvious upon actually reading of it, is that he says, no substance, all right, no substance is okay. Sure, no substance. And no state of motion can be attributed to this ether. Technically, even the no substance bit is a little bit questionable for the simple fact that he says, oh, this ether can be warped. Space-time can be distorted by mass. If there's no substance, i.e. it has no properties, then why does it have distortability? Well, we are waiting for Mr. Einstein to answer, but if he actually did, we would probably be more frightened than otherwise. For the simple reason that he's been dead for a long time. Now, supposedly, you cannot attribute a state of motion because his space-time is in 4 dimensions. The 3 dimensions of space and the dimension of time. Alright, so the metrics that lie entirely within the relations of these 4 dimensions cannot be measured for it. Well, for the movement of space-time over time. Because, well, it's within the same 4 dimensions. Wait a second. What is the propagation of light that his theory so depends upon? It moves through space-time. It moves through space over time. So, if you cannot attribute states of motion in 4 dimensions, then how can we measure even the progression of light? How can anything move? Okay, first, this is one wording hole, perhaps. But there are more. Now, his ether, space-time, is warped by mass. So this is the analogy that is typically used to teach students. This is how Einstein's idea of space-time works. And oh, your light will move along the curvature. Well, there's a few problems here. He says no motion can be attributed to this ether. No state of motion. No state of even relative motion. Okay. In case you haven't noticed, these disturbances move. Why? Because mass has this astonishing ability. It can move. So if the disturbance can move, and if the disturbance distorts space-time itself, then of course the ether has to move. Well, okay, that's one possibility. That's the second one that's listed here. The first one is that all mass energy somehow emits influence into the ether, and the ether moves with all mass energy, in a sense. So how much it's moving in a particular area depends on the nearby concentrations of mass energy. But this is a little bit more complicated. But an essentially co-moving ether like this is not excluded by most experiments. Now, if ether itself fluxes, then, well, first of all, suppose the presence of mass causes flux in space-time. This is correct, according to Einstein, and according to us. Now, if this affects the progress of events through space and time, and is related to the space-time coordinate relative to the space-time coordinate of the disturbance, i.e. the mass, then the disturbance distorts space-time in a particular region of space and time, which moves in space over time. And space-time itself cannot move despite the disturbance existing and moving. Sir, if you have a wave, that wave is moving. Sure, you can say the individual particles aren't moving sideways, but they sure are moving up and down. If Einstein's ether theory is correct, and there is no movement to be associated with this ether, then none of these disturbances that we see, which have moved, would be possible, nor would anything be moving. Alright. In addition, we must note that Einstein's most famous formula is not quite his. So, the first guy to propose the concept that perhaps, energy and mass might be the same was actually Sir Isaac Newton back in 1717. Then, well, took a while, but eventually Lorentz and Poincaré derived electromagnetic mass as this. Due to certain problems with this formula, work continued. For example, Poincaré was concerned, hey, if you compress an electron longitudinally as it moves faster and faster, and the volume remains the same according to Lorentz various formulas, then wouldn't the electron turn into a pancake and basically explode? So Poincaré was concerned about this, and eventually he decided that there had to be an internal energy of some sort, and he eventually got this formula, which directly becomes E equals mc squared. There were other scientists who were also working on this during this general time period. Interestingly, after Einstein essentially took Poincaré's work and ran with it, Planck actually criticized him, saying that it was only valid to first approximations. However, the first paper Einstein put out in 1905, his special relativity was his third one, and his E equals mc squared was his fourth one. The first one he put out in that year was essentially taking Planck's idea and extending it a little bit, which apparently the big guy, Planck, forgot to do. So, well, essentially he got Planck on his side, and so he got Planck's support, despite the fact that Planck did criticize some of his approximations. Now, given the concept of electromagnetic mass that was popular at the time, there were some obvious problems. So Lorentz himself hand-waved these problems. These problems were essentially that, if your ether, i.e. electromagnetic background, can push objects into motion or alter the motion of objects, which they do, light bends, then of course the ether has to receive a counterforce, right? Force and counterforce, reaction. Well, wouldn't that make the ether move? Well, wait a second, Lorentz insisted that the ether was stationary. So he said they ended up doing something about tensions, or tried to do something about tensions, until he realized, wait, tensions means that it can't be stationary anymore. And then Poincaré decided to use a fictitious electromagnetic fluid to try to accommodate this. Now, some people say that Einstein decided to take away the only property left to Lorentz ether, which was immobility. So Einstein supposedly took it away. The thing is, he did not. If Einstein took away the immobility of space-time, why then would he claim that no motion could be measured? If he did not insist it was immobile, then why did he say that no motion relative to any inertial frame can be measured? Because that's what it means when he says you can't measure the motion. Well then, it's not immobile, right? So there is no universal reference frame that is favored. Why can't we measure the relative motion of it relative to other frames? So he appears to be dependent on the same stealthy ether as the other guys, which is a problem. Alright. So this impenetrable stealth is not scientifically believable. We don't need to disprove these things. It's up to them to prove it. Now, Einstein didn't just stand on the shoulders of giants. He stood on the shoulders of everyone who came before, and he laid claim upon them. Einstein was a good synthesizer. He was also good at extending things. For example, Planck took 5 years, and he didn't connect his quantized energies to, well, the photoelectric effect. Which means that it was right for Einstein to step in and make the connection. Sure, but he also did a lot of things that were essentially taking the other guy's stuff, changing it up a little bit, and calling it his own. The problem was he apparently didn't realize his own immense logical conflict here. Now, Einstein very importantly derived or popularized at least, no, he didn't derive it, Poincaré did, but he popularized the time dilation formulas. A problem with his idea of his proof, which we saw earlier, is the fact that clocks measure events. So a clock, say, measures the dripping of water from a tap, a water clock. Or it measures the swinging of a pendulum. Sure, these are all valid proxies for time. But if you take this pendulum and move it to the moon, does that make time run any slower? No! Clocks do not dictate time. Perception doesn't dictate time either. So Einstein's concept was basically that with a fixed constant speed c, you take a light clock, and from the outside you see it run slower because it's all c as it goes diagonally. There's a few problems with this. First, the speed of light is, as with any other speed, distance divided by time. So Einstein says that the ratio for a particular form of mass energy between 3 dimensions combined, displacement, and their ratio to a 4th dimension, is more important than any of these dimensions. He insists on length contraction and time dilation just to make his math work out. The thing is, he's essentially insisting that one frame of reference, i.e. the photon itself, traveling through 4 dimensions is more important than any of the 4 dimensions. There is something to be said about the amount of hubris required to insist such a thing. And we do point out that all these equations were created by a man who was abjectly against Michelson-Morley. So we should point out that Einstein took formulas from a man who was in abject denial of Michelson-Morley. So what Einstein got stuck on was his idea that this diagonal, to the outsider, it looks like C. Therefore, well, he insisted it looked like C. Therefore, because this would look like C, the outsider must see the clock inside going slower. That's what Einstein said. The counter problem, which he did not consider, is that the insider must see the outsider as also going slower, and in reality, what the 2 clocks are doing are going at the exact same rate. Perceptions do not dictate time. If you see my clock ticking fewer times, that is your problem when I see my clock has in fact not ticked fewer times. Now we do point out that certain conditions may affect the rate of the particular things that your clock is measuring. But that's not quite our point here. Einstein says that the times must be different because of his postulate of C. We show the problem with C in the other videos. More importantly, even under Einstein's scheme, a clock looking different, what does it say about time passing? Well, okay, let's say I turn my clock back 5 hours. Or change the gears so it ticks in reverse. Well, I have not in fact invented a time machine. Or alternatively, my watch has not been tightened for a while. So it is moving really slow. My time goes the same as yours. Clocks looking different doesn't say anything about time passing. This is very important. Now, a clock measures events which it translates into the passage of time. So a scale measures the force of gravity, i.e. the weight, and translates that into mass on its indicator. This is very different from a balance. A balance actually does measure mass because it uses equivalence of weights. But a scale, which measures weight, is only a proxy for mass. A scale does not dictate the mass. It is not as if you take a person, put him on a scale on Earth, and then move him and the scale to the moon, and suddenly he has 1/6 the amount of mass. Similarly, a clock does not dictate time. Now, in conclusions and our proposition, Einstein's contradictions include: Einstein states that space-time is not immobile. Therefore, the local motion must be measurable unless Einstein's space-time is essentially Russell's teapot. This is grossly contradictory, by the way, to Einstein's own assertions and theory. This is a really important point. If he's already dropping the brick on his own foot, just with his words, well, and logic for that matter, there is no particular need to look at math equations that came out of a guy who could not accept Michelson Morley. Anybody who uses Lorentz to defend Einstein should reconsider before trying. Now, due to these problems, I find it completely ridiculous that any piece of space-time, i.e. be it you, a photon, or whatever, any piece of mass energy going through space-time is apparently more important than all 3 dimensions of space plus the dimension of time put together. So, that piece of mass energy must be incredibly arrogant to even suggest such a thing as it being more important than 4 dimensions together. Unfortunately, that is exactly what is asserted in Einstein's second postulate, that the speed of light relative to all frames of reference, and regardless of the speed of frames of observer or emitter, must be c. Now, in my vision, first, time is invariant. Proxies for the progress of time, such as the mechanics of a clock or periodic events, do not in fact dictate the passage or lack thereof of time. Now, nobody's perceptions, which are another proxy for time, dictate the passage of time either. No, for the record, for those who are still in doubt, sleeping does not in fact pause the universe. I'm pretty sure we all figured that out pretty early, right? I mean, I hope Mr. Einstein figured it out too, but given some of his statements, who knows? Anyhow, time must not be relative to any form of mass energy, not even c. So, because Lorentz was a guy who just couldn't overcome his obsession with a stationary luminiferous ether, or ether, whatever, all defenses of Einstein using Lorentz transformations are scientifically invalid, for the simple reason that Einstein began his theory on Lorentz transformations. So because A, therefore A is correct, is not science. Alright, I will once again make the note that in 2015, I was the first person to so thoroughly and comprehensively, by multiple methods, use thought experiments, math, and science to demonstrate that Einstein's relativity has fatal errors. So progress is forever. First, we had flat Earth. Then we had geocentrism. And then we had the idea that smoking was good for you. Now we will have Einstein's relativity. And from Einstein's relativity, we will get to reality. So thank you for watching, and for detailed proofs disproving relativity itself directly and mathematically, and by thought experiment, please watch my other videos.